Hey everyone, welcome to the Wherobots live stream. My name's Will. Today we're going to be taking a look at working with some cloud native geospatial data formats. Specifically, we're going to be working with GeoParquet and the Havasu spatial format, which is a spatial table format, which is an extension of Apache Iceberg. So if you've ever worked with Apache Iceberg or Parquet, we're going to be looking at adding native geospatial functionality to both of those file and table format concepts. So try to make this as interactive as possible. Let me know if you have any questions in the chat. Definitely also let us know where you're tuning in from. That's always fun as well. We're going to do a little bit of a mix of, I'll have a few slides that we'll start with just to introduce some concepts. But then the majority, I'd like to be kind of hands-on, working with code and working with data. So we'll do that in Wherobots Cloud with SedonaDB. So definitely, if you'd like to follow along, I'll share all the code and the steps to be able to do that. Cool. So let me share my screen here. So like I said, we're going to start with a few slides just to talk about some concepts as we get into things here. So first of all, this is the Wherobots live stream. If you're not familiar with Wherobots, Wherobots is a company that was founded by the creators and core maintainers of Apache Sedona. Apache Sedona is an open source distributed framework for large scale analytics of geospatial data. So you can think of Apache Sedona as extending the functionality of a distributed data processing framework like Apache Spark or Snowflake or Databricks, and adding functionality for working with native spatial types, so points, lines, polygons, these kinds of things. Also being able to work with raster data and extending the SQL functionality that we typically work with in these environments to add spatial functionality. We can also work with Apache Sedona in Python or R. Lots of options there, but really the core idea is large scale spatial analytics. And at Wherobots, we've built a managed cloud service that extends the functionality of Apache Sedona to give you cloud native functionality. So part of what we're going to talk about today is the Havasu open spatial data lake format that is available in Wherobots Cloud that again extends the functionality of Apache Sedona and really with a cloud native focus. And we'll talk a bit about what that means in a minute. So our two topics for today are GeoParquet and the Havasu table format. So let's talk a little bit, I guess, first, maybe a little bit of a compare and contrast of what these two things are. So GeoParquet is a file format. So if you're familiar with Parquet, GeoParquet is really a way of specifying how to store and work with spatial data, geospatial data specifically, in Apache Parquet. And Parquet is really known for efficient storage, so being able to efficiently store lots of data, reduce file sizes, but also efficient retrieval. So by chunking data in different ways, at query time, query engines are able to select only essentially the data that they need from maybe a large scale distributed group of Parquet files. So that's GeoParquet. Really think of geospatial data in Apache Parquet. And it's one thing to note about GeoParquet is we're talking about geometries or vector data. We typically don't work with raster data in GeoParquet. Now, the other thing we're going to talk about today is the Havasu table format. Havasu we can work with both vector and raster data. And Havasu extends Apache Iceberg. So Iceberg is an open table format. Really, the idea is to bring the developer experience that we have of working with SQL tables to this data lake environment. So being able to introduce things like ACID transactions, being able to insert, update, delete data, have things like evolving our schema, being able to do time travel to move back to a snapshot. Really, I think the goal of Iceberg is just to simplify and hide a lot of the aspects of working with a data lake where we're not thinking about how are we managing our partitions in our Parquet files. Really, we're just thinking about working with SQL tables. So those are the two things we're going to talk about today. Let's go a little bit deeper into this idea of GeoParquet. So GeoParquet, all about storing geospatial data in Apache Parquet. If we look at the goals of GeoParquet, it's really to identify workflows in the geospatial world that make sense for working with columnar data. So we should say that Parquet is a columnar file format. We'll see what that means in a minute here. And really to enable interoperability. So being able to work in different query engines with the same data, essentially. The GeoParquet specification, which I've linked on GitHub here, you can participate just by review the specification and some of the discussions there, all on GitHub. But the GeoParquet specification is being developed alongside the GeoArrow specification. So if you're familiar with Apache Arrow is a way of serializing in-memory columnar data. So being able to have very efficient sort of zero copy shared access to in-memory, in this case, geospatial data. And we'll talk about what that enables as well. So GeoParquet is really a community effort. There's a lot of groups involved here, from large cloud vendors to geospatial specific companies, things like Planet that provide satellite imagery, maintainers of geospatial libraries like GDAL and GeoPandas, and then also companies that are more focused on geospatial, like Wherobots, Alcevea, and so on. And again, anyone can get involved here. Just check out the discussion on GitHub. So let's talk a bit about Parquet, because I think there's some important concepts to understand in Parquet that before we dive into GeoParquet, it's important to understand some of these things to understand what are the benefits really of working with Parquet and then also GeoParquet. So we said that Parquet is column oriented. What this means is that column values are stored next to each other. This is really useful for analytic workloads where we want to say maybe grab all of the values of a column, do some aggregation, something like that very quickly, rather than row-based storage where we're getting a single value of each column in a row. That's sort of more of the like transactional workload. So column oriented for analytic workloads. And really some optimizations in Parquet enable efficient data storage. So by using encoding and smart compression, being able to reduce the file size that's stored, and then efficient retrieval. So at query time, by chunking data, can we only request the data that is necessary to render certain queries. So basically accessing less data perhaps over the network. And so for these two reasons, Parquet is very popular with cloud storage buckets. So a lot of folks are using something like AWS 3 to store Parquet files. So let's look at an example here. So imagine we have some data, maybe these are our users or employees, and we have something like an ID column, a name, age, and maybe a salary for each user or employee. And this is a simplification on the left here of how this data might look in Parquet. But basically, we're storing column values next to each other, and then we have some metadata about the file. And that metadata might include information about the types that are stored in each column, and some summary statistics, these sorts of things. So for analytics, if we want to grab, all of the salary values, we can skip to that column and grab all of those very quickly because they're all stored next to each other. And again, this is a simplification. We'll see what exactly we're simplifying here in a second, but just important concept to understand. So we said one of the benefits of Parquet is efficient data storage, leveraged through encoding and compression. And there's a few different options. Parquet is pretty smart about how this is done. So for example, delta encoding, if I have a sequence, maybe like an ID that increments one value in each row, rather than storing each individual value, we can use delta encoding to store the initial value and then store the offsets as we move along. We can also use dictionary encoding. So being able to take advantage of if we have repetitions. And again, this is a simplification. Parquet is actually much smarter about how to do this, but imagine we have dictionary values for the different names and ages that we're seeing. And if those are repeated, rather than storing each individual value, we can store basically the key for the value in our dictionary, like so, where we're, instead of storing the full string values for each name, we're just storing the key to a dictionary. And then we can also leverage things like run length encoding. If we have repeated values, rather than storing 42,000 3 times in a row, we can just store that value once and say, hey, that repeats 3 times. Now, efficient retrieval is one of the other benefits of Parquet. And really, to understand this, I think we need to take a look at removing that simplification that we saw earlier, where we're just storing all column values together. Really, Parquet files are chunked into what are called row groups. So we have sort of a selection of the rows that are grouped together. And then within each row group, we're storing values of each column chunk, they're called, together. And then we have metadata, which are summary statistics for each column in each row group. So we might have something like the minimum and the maximum for the age or for the salary. And what this allows us to do, I guess, 2 things really. One is to leverage projection pushdown, which means that at query time, if I want to select just certain columns, well, I can do that. I can skip reading the columns that I don't care about. That's projection pushdown. But also predicate pushdown, which means, let's say we're as part of our query, we're only looking at salaries that are greater than $100,000. Well, if I look at the summary statistics for row group 0, I can see the max ID, or let's say we're looking for IDs greater than 100,000. I can see that the max ID only goes up to 99,906. So we can exclude this row group and move on. We can zero in on just reading the specific columns in the specific row groups where the values of our data lie, depending on the predicate of our query. So that's predicate pushdown, which enables pruning pieces of Parquet that we don't really care about, depending on our query. So efficient retrieval. Okay, so that's Parquet in general. Let's talk about GeoParquet. So GeoParquet, we said, is just specifying how to work with geospatial data in Parquet. Really not necessarily trying to create a different specification, really just trying to specify how to work with spatial data in Parquet. And there's, I guess, two main concepts in the specification. Specification is not long. You can read it there on GitHub or the website. And really, the two main concepts are one, specifying how we should serialize geometry, so vector data in Parquet, things like points, lines, polygons. Uh, and the specification introduces a new geometry type and says that uh, geometry data should be serialized using well-known binary. There is also a proposal for a geo-arrow serialization that did not make it into the 1.0 version of the specification, but I think that will show up pretty soon here. Then the other concept is talking about what file and column metadata should be stored. So at the file level, things like the version of the GeoParquet spec that the file is using, we can store multiple geometry columns in GeoParquet. So specifying which is the primary geometry and then what columns are geometry columns. And then for each column, specifying what's the encoding. Currently, well-known binary is the only option for the encoding, and then the geometry types. So we can have multiple geometry types. We can mix points, lines, and polygons all within one column, but specify which ones we have available. So those are the required pieces of metadata. The other ones are optional. So things like the CRS, the coordinate reference system, the edges, whether we're working with spherical or planar data. And then this one I've put in italics because I think this is particularly interesting and useful, storing the bounding box of all geometries in this GeoParquet file. This is important because this allows us at query time, if we have data partitioned across multiple GeoParquet files, this allows us to prune certain GeoParquet files if the bounding box of the geometry doesn't fall within the spatial predicate. So let's say we're searching for data in a certain area, maybe by a polygon or something like that. Well, if we know the bounding box of all of our GeoParquet data in certain files is over here, we can only look for where that bounding box intersects the polygon where we're searching for data. So that allows us at query time for GeoParquet readers to implement this sort of data pruning to enable more efficient retrieval of GeoParquet data. So geometries are serialized as well-known binary in GeoParquet. This is kind of an example of what that looks like. So you may be familiar with well-known text, WKT, which is shown on the left here, which is just a way of having a more human-readable format for specifying a geometry. So we start with the type of geometry, point, line, string, polygon, and then an array or perhaps a nested array of the points that make up the geometry. In well-known binary, we're using a binary representation of that essentially. So we start off with some representation of what type of geometry, and then in binary, serialize the actual points that make up each geometry. And then the benefit of this is we have the encoding and compression options that make up Parquet to efficiently compress and encode this data for efficient data storage. So if we go back to our example, maybe we add a location column that gets serialized as well-known binary in our GeoParquet file. And then here we can see the metadata that's added at the file metadata level. Cool. So that's kind of the general idea of GeoParquet. If you check out the GitHub repository in the issues, there's some interesting discussions. There's a pull requests for adding things like we mentioned the optional geo arrow encoding. So this is really neat, enables zero copy integration with other spatial tools, libraries, visualization. So once we very, very efficiently deserialize that, load that into memory, we can essentially move that geospatial data back and forth between, say, something like GeoPandas and visualization library. There's an interesting visualization library from the folks at Development Seed called Lawnboard that leverages this idea of GeoArrow to render very, very large geospatial visualization. So millions and millions of points rendered in a Python notebook or in the browser, which takes advantage of GeoArrow. I was playing around a bit with that in a blog post and a tutorial last week, which I'll dig out and drop the link to if we have time. But that I think is really interesting development. There's also some discussion on how to add uh, row group level pruning. So we said that we can leverage the bounding box here that's stored at the file metadata level so that GeoParquet readers are able to prune if we have partitioned Parquet files, are able to prune that across multiple files at the file level. But could there be a way for us to be able to prune data at the row group level? So if we go back to our example here, if we added something like a minimum bounding rectangle or bounding box column to our data, that would then get picked up in the row group statistics, which would then enable GeoParquet readers to prune and exclude row groups based on the geometry. So that's currently in discussion. There are a few GitHub issues looking at different ways of approaching that, either by adding a column specifically, like a bounding box column specifically, or exploring options for adding spatial indexing. So if that sounds interesting, or if you have thoughts on that, definitely check that out. Cool. Okay, so that's enough of me talking, looking at slides here. Let's take a look at how we can actually work with GeoParquet data. I'm going to use Wherobots Cloud. So let me drop a link to this in the chat. And I'll also make sure that I am not missing anything in the chat here. We're streaming on both LinkedIn and on YouTube. Cool. I see Yusuf in there. Cool. Yeah. Thanks for joining. Cool. Okay. So I dropped a link to Wherobots Cloud. Wherobots Cloud, we said, is a sort of managed service for working with large scale geospatial data. Anyone can create an account at that link that I pasted to sign up, and you get sort of a free tier by default that exposes some basic level of resources good enough for development and testing. And of course, you can always upgrade to the professional tier, which just exposes more resources for working with large scale geospatial data. So once you sign in, you'll see a screen like this. You'll be prompted that there's a big start button to provision the notebook environment. So the notebook environment is the main way that we interact with our data and our programming environment in Wherobots Cloud. So I've already provisioned one. By default, it's the Sedona Tiny instance. But again, you have options for resources, runtimes with more resources if you upgrade to the professional tier. But it's nice to have that free tier to be able just to development and testing. So we're going to hit Open Notebook, and this will open the Wherobots Notebook environment, which is a Jupyter Lab environment. I think by default, you'll see this notebook, which is your first Wherobots Cloud notebook, which kind of walks through some ways of getting started in Wherobots Cloud with SedonaDB. querying data in the Wherobots open data catalog. Just kind of a simple example to get you started. What we're going to be doing is working with a notebook that I've already created here. If you'd like to follow along, the code is in GitHub. So I'll drop a link to this GitHub repository in the chat here. Cool. So I dropped a link to that in the chat. And if you want to follow along, I think the best way to do that, there's a couple of different ways to load notebooks into Wherobots Cloud. One thing we can do is just clone the repository. So if we copy the URL, go back into our notebook environments, and if we start up a terminal, we can just do something like git clone, and then the URL to the Git repo. I've already cloned this, so I'm not going to do that. But that would be what you'd want to do. And then on the file explorer here on the left, you would be able to see first would be this hands-on Havasu directory, and then in the notebooks, we're running this GeoParquet Havasu notebook. It's the only notebook in the repo. Cool. So let me zoom in a little bit here. So this is readable. So let's get started here. We're going to install one dependency, PyArrow. This is the Python implementation of Arrow that helps us to read Parquet files. There are a lot of dependencies installed by default in Wherobots Cloud. Lots of the geospatial libraries like GeoPandas and so on. But you can always install other dependencies. And then I'm going to import some packages that we're going to use here for some various things. So the first thing we're going to do is let's just take a look at an example GeoParquet file. So we're just going to grab this from the GeoParquet GitHub repo, and then we're going to inspect the metadata. So here we're just using PyArrow to read the metadata. Specifically, that's going to be the file metadata, so the metadata for the entire GeoParquet file. And then we're looking just at the geo object within the metadata. So GeoParquet adds this geo object as part of the metadata. And we see exactly the things that we mentioned earlier. So what's the version of the GeoParquet spec? What's the primary geometry column? Well, it's called geometry. For each column, for each geometry column, we have to say what's the encoding and what are the geometry types. Well, there's only one geometry column, and it's a mixture of polygon and multi-polygon. We're also storing the CRS, the coordinate reference system, specified using the proj.json format. And then down below that, we can see the bounding box of the data. And this looks like some pretty large scale data, but you can see this is a bounding box. So this is a bounding box of all of the geometries that are stored in this GeoParquet file. We can look at the actual GeoParquet file. So first we can see the schema. So we have numeric value, population, continent, name, our strings, and then here we can see the geometry column. This is stored as a binary. And then, like I said, with Parquet as a columnar format, all values are stored next to each other. So we can see this is a very small GeoParquet file. We have some information about some countries, and then we can see the binary encoding of the entire geometry column. Okay, so that's not super useful, but that gives us an idea of what that looks like in an actual GeoParquet file. So let's load this in SedonaDB. This is going to be a little bit of overkill loading this tiny GeoParquet file in SedonaDB, but I think it's helpful to understand sort of how we can work with GeoParquet in Sedona. So the first thing we're going to do to get started with Sedona and Wherobots Cloud is to configure this Sedona context. And one thing you'll see here in the configuration options are things like specifying access to cloud storage buckets like S3. We don't really need this. In this case, we're just going to be pulling down data in public buckets, but it's useful just to see what that looks like. We could put in, credentials or IAM, different ways of accessing our S3 buckets. So we're going to load this GeoParquet file. So Sedona implements a GeoParquet reader, and we're going to just load that here from S3. We're going to assign it to a view, so we can kind of treat this as something we can write SQL queries against, like a table. But here we're just looking at I guess this is the entirety of the data set. So we have geometry for each row, name, continent it's on, and so on. So pretty small. We can also look at the schema, and we can also visualize this data using Sedona Kepler, which is the Kepler integration for Sedona. So we just pass a Sedona data frame, and we have the Kepler interactive visualization for working with this data, which is quite neat. Okay, we can also just start to work directly with this data using spatial SQL. So what's nice about GeoParquet is the geometries are serialized as geometries. So for a GeoParquet reader, when we load those, we don't need to transform those into, in this case, polygons and multi-polygons. Those are recognized by the GeoParquet reader as the native geospatial types. So here, for example, we can just start using spatial single functions. Here we're calculating the centroid for each of these polygons. So there's lots we could do to work with GeoParquet files for analytics in Sedona, but one of the things that is a great use case for Sedona is being able to create GeoParquet files. So we're going to load a data set from S3 into a new data frame, and this is CSV data. This is a data set that I've used before from BirdBuddy. You may have seen an example or two that I put out with this data set. So BirdBuddy, these are smart bird feeders that have image recognition that can identify the species of the bird and the location of the bird feeder, and then share that data publicly. And you can download that data here. It's a fun little data set to play with. So we're going to use that as our example. So we're pulling in a CSV of this data, and then we're going to cast it to a point type so that we have an actual point geometry to work with. So we can look at the schema. We can see, yep, we have geometry. We have the timestamp, and then the common name of the species and the scientific name of the species. I grabbed just 5 million observations here, which is still fairly tiny for working with Sedona, just to have a sample data set to play around with, but we can certainly work with much larger scale data in Sedona. So we can do things like filter for birds by species name. We can visualize those in Sedona. So here we've filtered for the mountain chickadee using just SQL here, and then pass that into Sedona. So we can see all of the sort of the range of the mountain chickadee, which, yep, seems like he likes to stay in the mountains here. So a common analysis that we might do with this type of data is do something like calculating the range of each species. So we could do this by calculating a convex hull. So if we do an aggregation, if we group by the name of the bird species, and then union those geometries together and calculate the convex hull, so a polygon that captures all of the point geometries, we can visualize the range of each species as a polygon. And Kepler is nice because we can do things like style, fill color, based on the name of the species. Let's maybe not have such a dramatic color here, maybe something with more distinct color palette. There we go. So then we can see, okay, here's the range of the eastern bluebird. Yep, that's in the east. Here's our Sellers Day range, our mountain chickadee, and this is the California towhee, which yeah maps pretty closely to the California area. So that's neat. That's one type of spatial analysis that we could do with this type of data. So question from Yusuf in the chat: if Sedona Kepler is using the new GeoArrow drivers or displaying data through JSON CSV. So I think what it does is serializes to a geodata frame and uses GeoJSON to render that. But I think that's definitely something to look at. Would be the new GeoArrow drivers in Kepler. Thanks for pointing that out. That would be something interesting to explore. Okay, so we saw the data we're looking with. We saw some basic type of analysis we might do with that data. Let's take a look at how GeoParquet fits in. So let's save this data as GeoParquet, and we'll see how to do that using Sedona. So to do that, we're going to save this to S3, and by default, in Wherobots Cloud, we have access to S3. We can go into the Wherobots dashboard. And if we look at the file browser, we can see here there are a few different directories. Notebooks, this is where our notebooks are stored. Let me zoom in, make this a bit bigger. The data directory. Now, this is going to be private to either our organization. We can have organizational accounts in Wherobots Cloud and have users that are members of an organization and share data that way, or we can have data specific to our user. So here I've uploaded lots of different files, and we can programmatically access this through the notebook environment. By default, there's this user S3 path. So this is private to our user in Wherobots Cloud. So we're just grabbing that with the environment variable. And then here we're going to save a single GeoParquet file. So we're going to repartition to a single partition just to make sure we're saving one single GeoParquet file. Sedona has a built-in GeoParquet writer, and we're just saying where we're going to save this. We're going to save it in our Wherobots S3 under GeoParquet birdbuddy.parquet. And if we go inspect that file, we'll see that it's only 40 megabytes. If we compare that to the original CSV file, it was 400. So we can see there's lots of compression and encoding that's happening there, which is pretty impressive. So we've saved this as GeoParquet. We can also read it. So pointing to that exact same file, we can use the GeoParquet reader in Sedona to load that data directly into a data frame. What's nice is that we don't need to cast that explicitly to geometry type. That data is loaded directly, since we serialized that in GeoParquet as geometries. So that's quite nice. Let's do a little time comparison here. So let's do a filter. We're going to filter for observations that are within this polygon. This is roughly, I think, the area of around Phoenix in Arizona. And we'll do a comparison. We'll compare the time that it takes to load the CSV version of the data and the time that it takes to load and apply that spatial filter to the Parquet data. And we should see that the Parquet data is faster, but I think because of the size of the data set that I chose, we don't really see much difference here. I think this would be more impressive if we had a larger data set, so that the compression would be significantly more. But anyway, what we should see here is, the loading the CSV data has a certain amount of overhead, and loading the Parquet data should be faster, simply because we're loading less data. Now there is a bit of overhead involved here. So again, we're just looking at 5 million rows. I think if we had much larger data set. So the example that I was using last week was the global fishing watch data, and we saw basically a 10x difference. And that was a data set of 23 million observations. So when we're creating GeoParquet files, one thing to think about is how to spatially partition the data. Now, let me go ahead and run this, and then we'll talk about what we're doing here. So what we want to do is, rather than store a single Parquet file, right? Because we typically are working with large scale data where we have, maybe something like terabytes, petabytes of data, billions of observations, maybe more, not just 5 million observations. And we want to distribute those across multiple Parquet files, because we're working with just one single file is not going to be performant. But the question comes up of what do we choose as kind of the option for partitioning? And there are a few ways to approach this. So we'll look at a few different approaches here. Typically, if we're working with maybe something like census data, or data where we have some like state, country code, something like that, we could partition by that, and that would give us some spatial partitioning. If we don't have that, as in this case, we can maybe use a geospatial index to partition the data. So one option to do that is to use a geohash. Geohash, I found a blog post that I think does a good job of explaining this. This is from Ben Feifke in the Towards Data Science publication, looking at a few different geospatial indexing options, including the geohash. So what geohash does is basically put a grid over the surface of the earth, and we can choose, at what level, like how fine grain of a grid we want to create. And so in our case, I use level 2 of the geohash. And so the way this works is we grid the earth and then grid each one of these grids, and we keep going down and recursively until we have however many characters. So a geohash creates a string, which we can use as the index value. Geohash has some issues though. It uses a Z order curve to lay out the grid, which means that we may have geohash values next to each other. So if we look at the jump here from 7 to 8, well, the data here is not necessarily in close spatial proximity, but the geohash value is in close spatial proximity. So that's not optimal. That's one of the downsides of geohash. So now if we take a look at how to use geohash as our partition key for partitioning GeoParquet files across many files, we first just create a geohash column, and we use the stgeohash spatial SQL function to do that, passing in the location, which is our geometry, and then the level. So we want to go level 2, which gives us 2 characters in that string for the geohash. And then to save that, we'll say let's repartition by geohash and use the built-in GeoParquet writer to again save that to S3, this one called BirdBuddy geohash.parquet. And if we go into our file browser, save this in GeoParquet, this is BirdBuddy geohash parquet, we can see how those are partitioned just by geohash equals and then the value. And then inside we have a GeoParquet file split across many different partitions. And if we look at the performance of that, so here we're loading and applying that same spatial filter to find observations within that area near Phoenix, we do see a noticeable difference here, 1.86 seconds. And the reason for that is the Sedona GeoParquet reader is able to exclude any GeoParquet files where the bounding box of the geometries, so essentially that geohash grid where that doesn't overlap with the polygon that we're searching for, Sedona can just exclude all those files and not look at them, only zero in on the one that has the data in the area that we're looking for based on the file metadata in the GeoParquet file that specifies the bounding box of all the geometries in that GeoParquet file, which is quite neat. And so here we do see a noticeable performance improvement, and this would be even more significant if we were using larger scale data. This is again a pretty tiny data set. So another option for index choice for partitioning GeoParquet might be the S2 index. If we go back to that blog post from Bin, we saw that one of the problems with GeoHash is the fact that we use this z-order curve. So we may have some spatial proximity issues where we're sort of jumping from one grid to another across a large area of space. With S2, which was an indexing method for geospatial data developed at Google, we eliminate some of the problems with GeoHash. So one is that we use a Filbert or a Hilbert curve, which is sort of a more curved way of moving through our grids, and we don't have that sort of jump across spatial proximity. And then the other is that it uses a different map projection, this unfolded cube map projection, so that we don't have distortions in the data at extreme latitudes, which is quite neat. The difference is that rather than getting a string value with incremental numbers of characters where we can sort of chunk off a character that represents a larger grid, we don't sort of have that same concept in S2. So now we do something very similar. We use the S2 cell IDs spatial SQL function. This gives us an array because if we were using a polygon geometry, the polygon geometry might span multiple S2 cells, but of course we're just using point geometry that's just going to be in one cell. So we just grab one value from the array that's returned, and we write that to a partitioned GeoParquet file, partitioned by the S2 value. We read that back and then apply the same spatial filter, and we can see some noticeable performance improvement here. And this could be just because of the way that we have partitioned, that the number of partitions, choosing sort of the resolution level with these geospatial indexes kind of depends on the distribution of your data. You kind of want a more even distribution of data. You don't want to have just a few very, very, very large Parquet files. Obviously, if the bounds on each GeoParquet file are smaller, we can trim more files. But that's going to be a bit of sort of the balancing act. So here, let's look at partitioning by administrative boundary. So we're going to load the natural Earth state and province data. And what we're going to do here is do a spatial join on our bird buddy observations to find out what state and province they lie in. So we're using st intersects to join the administrative boundaries with our bird buddy data, and we're just grabbing the name of the state. So for each observation, we have the location where the bird was found, the timestamp, the name of the species, and then the state or province code. And we can look at how many states and provinces we have in the data set. When I was first working with this data set, it was mostly focused within the US, and which is why I initially had chosen the state and province level. But then I think BirdBuddy has expanded its market share now, perhaps globally. And so then I realized, well, there are actually 851 states and provinces that we're finding observations in, right? So quite a bit in Europe. But if we look at the counts, like we're getting quite a few more in the United States. So for this tiny of a data set to partition across 851 Parquet files, we're going to introduce more overhead in working with that data. So I don't think that it makes sense to partition, in this case, given the size of the data, across this many partitions. But maybe country might be an option. But the downside of that is they're going to be mostly concentrated within the U.S. Partition. So kind of a balancing act. I'm going to skip writing the file, but I already did create this at the state and province partition. We can look at the timing, and yeah, it takes almost 8 seconds because of the overhead of reading across now all of these different 851 partition Parquet files. So we really didn't gain anything that way. Okay, cool. So that's a look at GeoParquet, how to load GeoParquet in Sedona, how to create GeoParquet files, and a look at various options for spatially partitioning GeoParquet files and some of the trade-offs of and when we do that. Let's go back to our slides here, because I want to talk a bit about the Havasu spatial table format. So we said earlier at the beginning that Havasu is an open table format for working with spatial data that is built upon Apache Iceberg. And we said that Iceberg is this open table format for analytic data sets that really gives us this reliable and expected SQL interface, working with SQL tables, kind of the way that we would expect SQL tables to work with. We don't have to think about how are our Parquet files partitioned, how can we optimize that. The Iceberg layer takes care of that, and we simply expose this SQL table layer for working with the data. So Havasu is an open source specification of how to work with spatial data in Iceberg. We can work with both geometry and raster data types. We're storing spatial metadata in the Havasu table based on the attributes of the spatial data that we're working with, but it's compatible with GeoParquet. So spatial data is encoded in Parquet, consistent with the GeoParquet specification. Of course, with GeoParquet, we don't work with raster data, so there's a slightly different format for working with raster data when we store that in Havasu. I should say there's two options for storing, for working with raster data in Havasu. There's the InDB option where we can store the actual raster values in Havasu, and there's an outDB method which is just kind of maintaining a pointer to that raster data. So if we're working with something like large scale GeoTIFF, cloud optimized GeoTIFF, we can just reference that in S3 rather than duplicating the actual values. So what are the benefits of using Havasu? Well, similar to the benefits of Iceberg is we have this like DBMS experience, introducing ACID transactions. So being able to work with upserts, deletes, inserts, these sorts of things, enforcing spatial integrity at write time, and then performance optimization. So being able to look at the spatial statistics of Parquet files to prune irrelevant data, and also being able to lay out and optimize how the underlying Parquet files are stored to spatially index that data. Cool. So let's go back to our notebook here, and we'll see how to work with Havasu in Wherobots Cloud. So first thing I'm going to do is drop this table if it exists. I think I've probably already created this. I ran this notebook before. So the top level namespace with Havasu and with Iceberg is called a catalog. And by default in Wherobots Cloud, there's a Wherobots catalog that is set up for us that maps to our S3, our private Wherobots cloud S3 bucket. So let's create a table where the schema matches the bird buddy data. So we're going to create a bird buddy observation Havasu table. So we have location, timestamp, and then the common name, scientific name of our species. So schemas or databases are kind of one level down from the catalog. So we have the bird buddy and then the testDB schema. We can look at the tables in our bird buddy database or bird buddy schema. We just created this one called observations. I have another one called feeder observations. We're going to ignore that. We can look at the schema, the describe table. So if you're familiar with SQL, these are very standard common SQL functions that we should be familiar with if we've used SQL a lot. We can insert data. So let's insert one value and we're going to create a geometry type. So at this point, at this current time, we observed a purple finch. I won't try to pronounce the scientific name. Okay, so we've inserted that so we can query our data using SQL. And so here we're just grabbing all observations from our table. And then we can visualize that in Sedona Kepler. Here's our one single bird observation. This is somewhere in Manhattan, I think. Just kind of picked a location at random in Manhattan. And then we can also write data frames. So let's write our Sedona spatial data frame that we imported previously. Let's now write that to append to our table. So now we've added those 5 million observations to our table. So we said earlier that Havasu can leverage spatial filter pushdown using the spatial statistics of the storage files of the Parquet files, and in order to leverage that, we either need to partition using some spatial key, or we can use Havasu to create a spatial index for us. And essentially, what this does is it is going to rewrite. Let me go ahead and run this while I'm talking about it. It's going to rewrite our data sorted by spatial proximity using a Hilbert curve. So we saw an example of that Hilbert curve earlier. So what this means is that all of our observations now, our bird observations, they're going to be sorted by spatial proximity. So ones that are close are going to be close to each other. And then when our files are partitioned, we're going to have partitions with data close to each other. So that means our bounding boxes, the spatial statistics in each GeoParquet file are going to be as compact as possible, so that at query time, we're able to prune more data files to efficiently apply spatial filters. And we can see what that looks like if we go to our file manager in Wherobots Cloud. We go into our customer directory. By default, this is our Havasu tables are stored in this warehouse directory. And this maps to databases, that maps to tables. And there's some metadata stored in JSON. If we go into the data directory, we can see these are a bunch of Parquet files that are partitioned for us. So we didn't have to think about that. That was handled for us by the Havasu layer. So we can do things like search for observations within some distance of a point. So here we're creating a buffer around the same point of where we said we observed the purple finch earlier, and then filtering to find all observations within that buffer. So let's compare the performance of that same spatial filter that we applied earlier. We were searching for all observations within a polygon And let's time that. And I think we should see something comparable with the other partitioned GeoParquet options. And again, yeah, so a little over 2 seconds. And again, the data set we're using is quite tiny, so we're not seeing much benefit of that partitioning, simply because we have some of that basic overhead of reading files. But I think if we applied this to a much larger data set, we would see the benefits there. So this example, by the way, was just looking at vector data, at geometry data in Havasu. There are some other examples. So when you sign in to Wherobots Cloud in this notebook example directory, you'll have these example notebooks. And we can see also some examples for working with raster data. Let me switch kernels here. I think this is quite interesting. And we'll run this. We're a bit out of time here. I have a meeting I have to jump to soon, but I just want to point this out to show that we can also work with raster data in Havasu. So this example is going to load a geotiff of aggregated world population, tile that, then load vector geometry to essentially look for population within a point geometry. So being able to work with both vector data and raster data together, I think is quite powerful in Sedona. So anyway, that example is there. I think we covered everything we wanted to in the slides. And again, I'll update the recording description with the GitHub repository. All this code is in this notebook here. But thanks everyone for joining. We're going to do these roughly once a month, and so as you have more interests in geospatial data with Sedona and Wherobots, let us know. Are there certain types of data sets that you'd be interested in seeing us work with? Are there certain workflows, certain types of analysis you'd like to see? Let us know in the comments. I think the next month for the live stream, we're going to focus on working with raster data in SedonaDB. So we will take a look at that and definitely be sure to subscribe to us on YouTube to be notified that we stream both on YouTube, or also follow us on LinkedIn as well to catch that. Great. Well, that's all for today. Thanks everyone for joining, and